While I'm doing that, please go ahead and also open up your notes and raise your hand. Here's the link if you are one of my students. Here's the link if you are one of Mr. Bangle's students. Remember, you can do your notes at any time and still get notes credit. However, if you do them during class, you'll get both notes and attendance credit, assuming that you're on time, actually doing it during class, and that you pass it during class. Excellent. Thank you for all that participation up there. Beautiful. All right, let's go ahead and talk a little bit about these. So the two groups that are the most reactive, again, the ones that are closest to being stable without actually being stable. Remember, when we talk about stability, we're talking about the octet rule. So tell me in the chat box, atoms want how many valence electrons? Tell me in the chat box. Think about that octet rule. Octet rule. Yeah, so atoms want 8 valence electrons, 8 outer electrons, and that would make them stable, right? So the only one up here that is stable is which group? Tell me in the chat which group is the only one that is already stable. Take a look at their valence electrons. Tell me in the chat which group has all 8 of its valence electrons. Excellent. I see Micah in the chat. Go, go, go. Tell me in the chat which group has all of its electrons. Yeah, exactly. So group 18 has all of its electrons. This one is stable. And so this one is actually not going to be reactive. So this one's not reactive at all because it's already stable. Again, we're looking for the groups that are close to stable, but not already stable. So taking a look here, you are absolutely correct. Group 1 will definitely be highly reactive because it only, tell me in the chat, does it need to gain or lose 1 electron? Gain or lose 1 electron? Tell me in the chat. It has 1 electron. Is it going to prefer to gain or lose that 1 electron? I see Micah in the chat. Get some more participation. Hello, hello. Will it prefer to gain or lose that 1 electron? Yeah, it's going to prefer to lose its 1 electron, right? So this one will prefer to lose 1. All right, and down here, group 17 has 7 valence electrons. All right, so it's pretty close to having 8. So tell me in this case, group 17, will group 17 prefer to lose or gain 1 electron? Will it prefer to lose or gain? Lose or gain? Tell me in the chat. Thank you, Micah. Yeah, this one will prefer to gain 1 electron, right? So again, it doesn't necessarily matter whether or not they're losing or gaining electrons. It matters how many they're losing or gaining. So group 1 and group 17 are the closest to being stable because they only have to do something with 1 electron, right? Every other group here, besides our noble gases, but every other group here has to either lose more or gain more than groups 1 and group 17. So that does make them the most reactive. Excellent job on that, everyone. Let's go ahead and go over some announcements.
So, as always, guys, please be sure to not share any personal information during class. We will require your participation as always, and these Class Connect sessions are always recorded for learning purposes. All right, so today, guys, we're right in the middle of the week. We're on Wednesday. Tomorrow is going to be a recording day, as always, and then we'll pick up with our schedule on Friday for one last project work day, which is also when the project will be due. All right. What we're learning today will help you with your project. We're learning about something new called electronegativity. So some words in there such as like electron or negative. Maybe the more negative you are, the more you attract electrons. All right, something like that. But we're going to be talking about it specifically in the trends of a period, right, or a row. All right. Today, the tasks we have are to define electronegativity and its overall trend on the periodic table. We're going to identify which atoms in the period are more electronegative than others. And then finally explain how electronegativity changes based off of atomic size. All right, believe it or not all atoms are the same size. Some are bigger and some are smaller. All right, so go ahead, guys. I want everyone to be raising their hand for their notes so we can move on.
All right, here is the link if you are one of my students. Here is the link if you are one of Mr. Bangle's students. We already sent these out a few times, so you have 20 more seconds to get this open and raise your hand. If you're on your phone, send us a chat. Everybody else, though, please raise your hand.
We're going to start off with a bit of a brainstorm just to get thinking about what we're going to learn about today. Go ahead for me, write in chat, starting with the first question. How many protons, based off of the periodic table we see up here, that silicon has? Remember, the protons are the atomic number. Correct, yeah, it's going to be 14. So silicon is 14. Now let's look at phosphorus. What about phosphorus right next to it? Yes, it has 15 protons does sulfur have. All right, so let's take a look at the last question at the bottom and turning on our whiteboard tools, making sure that we put a box around either decreases or increases. What would you say the trend would be as we go from right to left on the periodic table? Does the atomic number or the protons increase or decrease? Awesome, good. So this is the trend that we're noticing, right? The protons or the atomic number is increasing as we go from left to right. This is going to be something that's going to relate to electronegativity because electronegativity has a similar trend in which it increases or decreases as you go and move a certain direction on the periodic table.
All right, so let's talk a little bit about what this trend that we're talking about today is, which is electronegativity. Taking a look at the root word here, which of the three subatomic particles do you think this is related to? Protons, neutrons, or electrons? Go ahead and tell me in the chat box. Take a look at the root word of electronegativity and tell me, what do you think it's related to? Protons, neutrons, or electrons? Thank you. I see Micah in the chat. Work quickly. Let's get some more answers. Haven't heard from Stephanie or Daniela in a while. Jessica, get your answers in the chat. Yeah, exactly. So this is going to be related to electrons, absolutely. Specifically, electronegativity is the ability for an atom to attract electrons. And electronegativity is going to increase, the pattern is that it increases as you go up the periodic table and to the right in the periodic table. So you can see here that we go from francium on the bottom, which is bottom left, which is the least electronegative, all the way up and to the right to fluorine, which is the most electronegative. Now, what this means is that fluorine, again, as the most electronegative, is going to attract electrons very, very strongly, and as a result, it wants to gain electrons. Now, we already know this. It's in group 17. It has 7 electrons, and so it just needs one more. So it's going to pretty aggressively try to gain one more electron. All right, so let me write that up here. One more electron. All right, and so again, fluorine is highly, highly reactive. Francium, on the other side, is the least electronegative. It attracts electrons very poorly. Now, this does not change the fact that francium is still very reactive, just like we talked about yesterday. All right, so even though it has the least electronegativity, it actually is still very aggressive and very reactive. It's just going to do it in the opposite way. So it actually does not want electrons, and therefore it aggressively tries to lose electrons, right? It's in group 1, so it only has 1 electron, so it's going to try to lose 1 electron to drop down to a shell that's already full. Okay, so that being said, again, both of them are both highly, highly reactive. It's just they're reactive for different reasons. Go ahead and give me a smileys or emojis in the chats, or yeses if that makes sense. Smileys, emojis, yeses. You will notice, though, that I did actually ignore this one column all the way to the right, group 18, and that is our noble gases. Tell me in the chat box, why do we exclude the noble gases? Their valence shell is completely what? Tell me in the chat box. We haven't yet started, so don't worry. We haven't started the notes yet. Noble gases, their valence shell is completely what? Awesome. I see Micah, Landon on top of it. Yeah, they're in group 18, which means they have all 8 electrons, right? Group 18 has all 8 valence electrons, according to our octet rule, right? So they are completely full. So if they are completely full, do you think that they will want to do anything with electrons? Do you think they're going to want to lose or gain electrons? Yes or no? No, they don't care about electrons, and so as a result, they have no, we don't really talk about electronegativity with noble gases because in general, they're not trying to gain electrons or lose electrons. They're completely neutral. They just want to stay the way that they are. So again, the pattern is as you go up and to the right, electronegativity increases with the exclusion of noble gases. So if you're ever looking at noble gases, you see group 18, ignore group 18. Okay, now let's go ahead and fill in number 2. The first blank is attract. The second blank is full. Capitalization does not matter, but spelling does. Make sure you spell these correctly. You have 30 seconds to fill in both blanks for number 2 and raise your hands. What we're going to go ahead and take a look at is specifically today we're just looking at periods. Tomorrow we're going to look at groups, which are the up downs, but for today we're only going to look at left right. All right, so we want to think about moving left to right within the same period or row. What is happening to electronegativity? Now I do have a diagram up here, but I'm actually going to show it to you up on ptable.com. As always, I highly recommend that you are bookmarking ptable.com. Awesome, Julie. Highly recommend your bookmarking ptable.com just because this will be used for your project. All right, so you're going to need to be looking at the electronegativity of your element in your project. So it's good to have it ready to go and to know how to use it. So let's go ahead and take a look here. We have our periodic table. And the cool thing about this is you have a bunch of properties over here on the left. And if you click on those properties, you can actually see the periodic table in terms of those properties. So I'm going to go ahead and click on electronegativity. Okay, and now you can see that my periodic table has changed to show me electronegativities. All right, so what you can see here is that the yellow colors have less electronegativity, that's a minimum, and the brown colors have more electronegativity, that's a maximum. So taking a look here, as we go from left to right in a row, we want to think about what's happening to electronegativity. So tell me in the chat, which side has more electronegativity, the left side of a row or the right side of a row? Again, yellow is less, brown is more. Tell me in the chat, which side has more electronegativity, the left sides or the right sides? The left sides or the right sides? Tell me in the chat. Yeah, so definitely, as we look more and more towards the right, we can see that these elements on the right sides of our rows tend to be much darker, and that tells us they have much more electronegativity. Now, I know you probably can't read the numbers very easily, but fluorine has an electronegativity of 3.98. That's the highest on the periodic table, whereas over here on the left, lithium only has an electronegativity of 0.98. So 0.98 all the way to 3.98. So again, fluorine, highly electronegative. We already talked about that a lot. So fluorine is going to aggressively try to gain electrons. It's very attractive, very electronegative. Lithium is very unattractive to electrons. It's going to aggressively try to lose electrons. It has one. It's going to try to get rid of that one electron. All right, so let's go ahead and talk about this in terms of the diagram that I had for you. So let me go ahead and stop this. All right, so that being said, on the whiteboard, then box for me as we go left to right within the same period. All right, so let's take a look here at this period, for example. As we go towards the right within the same period, what's happening to electronegativity? Is it decreasing, increasing, or staying the same? All right, we already answered this together basically, but let's go ahead and make sure that we box it up on the board and begin to reinforce that learning. As we go to the right, think about the right side. What's happening to electronegativity? Is it decreasing, increasing, or staying the same? You can see here that the electronegativities are written up on the board. Go, 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 get your answers up on the board. Yeah, absolutely. So as we go to the right side, we can see that fluorine has a very, very large electronegativity of almost 4, whereas lithium has a very low electronegativity of only around 1. All right, so it's definitely increasing as we go to the right. This is the answer to number 3. Go ahead and raise your hands. Again, with the exception of noble gases, electronegativity increases to the right. You have 20 seconds to fill in the blank. With the word increases, capitalization does not matter, but spelling does. Oh, sorry, I did want to mention, again, on the left side, they have low electronegativity. This doesn't mean that they're not aggressive. They are still aggressive. They just prefer to lose electrons. Whereas on the right, with high electronegativity, highly attractive to electrons, they prefer to gain electrons. So again, the pattern is as you go to the right, electronegativity increases, with the exception of group 18, our noble gases. Let's go ahead and start to practice this.
Here is asking us which of these elements is likely the most electronegative. So we conveniently have them here all in a row for us, going from potassium all the way to vanadium. All right, please put a box around the one that is the most electronegative. All right, we'll go ahead and pause that for a second. All right, yes, so most of you had the correct idea. Vanadium is the most electronegative element we have on this selection from the periodic table. It is because it is the furthest to right, i.e., but without being a noble gas. So remember that little exception there. You have to be furthest to right without being a noble gas. All right, so the correct answer is vanadium. Please go ahead and mark this for number 4 in your notes. Go ahead and raise your hand when you're ready to move on. And let's move on to some more practice. Okay, so now most electronegative from this selection. Remember, farthest to the right without being a noble gas. Remember that hint, as it will be important. All right, we'll go ahead and pause that. And yeah, good job, guys. You did not get tricked by our trick question. Bromine is the furthest to the right without being a noble gas. So therefore, it should have the highest electronegativity out of all of these. All right, go ahead and mark bromine for number 5 in your notes. And once again, raise your hand when you're ready to move on.
All right, question number 6. Which of these elements is likely the most electronegative? Remember that pattern, all right? Think about that. Again, think about that tricky one as well. Please raise your hands for number 6. If you need help, we're in the Q&A area. Go, go, go. Raise your hands. You have 30 seconds for number 6. All right, so let's go ahead and talk about why this happens. So we've learned the pattern, right? As we go left to right, further to the right, electronegativity increases. It becomes more attractive to electrons, with the exception of our noble gases, group 18. But the reason why has to do with the size of the atom. So a smaller atom can actually attract electrons better. The reason why is because it has less space to reach through to try to get new electrons. All right, so think about it this way. Think about how smaller electrons are cuter, much like how a puppy is cuter than a big dog. And so a puppy is going to be more attractive and better at getting attention than a larger dog, although large dogs still do get attention, all right? But the smaller you are, the more cute or attractive you are. And so that is true for our atoms, okay? They are going to be able to attract electrons better. Now, the reason why, we'll talk about why on the next slide too, but the reason why is essentially when you're in the same row, all right, so if you're all in period 2, all right, if you're all in period 2, for example, you all have the same number of shells, right? So you have 2 shells. If you're in period 3, you have 3 shells. Period 4, you have 4 shells. So when you're in the same period, you have the same shells. Essentially, you look very similar to the other elements in the same row. But as you go left to right, you actually get more and more protons in the center in our nucleus. And protons are what are attracting that shell, all right, that valence shell. And so as you get more protons, you actually become more attractive to the same exact valence shell. And so you're going to pull in the valence shell more and more, making yourself tinier and tinier. And as you get tinier, you get more attractive. Again, let's go ahead and take a look at ptable.com because I want to make sure that we are used to using ptable.com, especially for our project. Right? So same thing here. I'm going to go ahead and take a look. This time we're going to take a look at the radius. Right? So I'll click on radius. And again, we said that the smaller you are, smaller or cuter that you are, the more electronegative you are. So what I want to see is in a row, which atoms are smaller, the ones on the left or the ones on the right. The light blue is small and the dark blue is big. All right, so go ahead and tell me in the chat, right, which side, left or right, has the smaller atoms? Which side has the smaller atoms? The ones on the left side of our rows or on the right side of our rows? Absolutely, yeah. So as we go further into the right, you can see it gets lighter and lighter blue. Again, I know you can't actually see the numbers, but fluorine has an atomic radius of 50, whereas lithium all the way on the left has an atomic radius of 145. And again, this is an opposite relationship. Fluorine is really small, and since it's really small, it actually has a really big electronegativity. It's the cutest, it's the smallest on the periodic table, it is the most electronegative. Go ahead and give me a green check or an orange X if that's beginning to make more and more sense. Again, the smaller you are, the more to the right you are, the more electronegative you are. All right, so we know the pattern, and now we're explaining why that pattern exists. And let's go ahead and then fill in question number 7. A smaller atom can attract electrons better. Again, fill in that blank with the word better, only the word better. Make sure you spell it correctly. Capitalization does not matter, but spelling does. 20 more seconds to raise your hands. So let's go ahead and take a look at an example of how of what's happening here, because I know it's kind of hard to visualize why it's really shrinking. So let's go ahead and take a look at a real example here. So carbon and nitrogen are both in the same period. All right, so they're both in period 2. You can see them right here. Here's carbon and nitrogen. And as a result, they have the same number of shells. Take a look down here, the green shells. How many shells do both carbon and nitrogen have? How many shells do they both have? Tell me in the chat. Yeah, they're in period 2, and so they also have 2 shells, all right? So if you're in period 2, you have 2 shells. And the result is they look very, very similar to each other. Smiley faces emojis in the chat if you can see that they have very similar structures to each other, right? They have a nucleus, they have 2 shells, they look very similar to each other, okay? Smileys, emojis, thank you. Monse, thank you. Daniela, excellent. Now, the difference, though, is the number of protons that they have in the center. So carbon only has 6 protons in its nucleus, whereas nitrogen has 7 protons in its nucleus. And again, that comes from its atomic number. Carbon has an atomic number of 6. Nitrogen has an atomic number of 7. But again, they're both trying to pull on the same exact valence shell. They're both trying to attract the same valence shell. Well, we know that protons attract electrons because they're opposites and opposites attract. So if you have more protons in your center, that means you have more positivity to attract your negatively charged valence shell. Again, the same valence shell. All right, so because nitrogen has an extra proton, it's actually better at attracting that outer shell more, and it's going to pull it in and it's going to shrink it down. So that will make it smaller. And again, the smaller you are, think about how this makes it cuter, like a puppy, and therefore it's actually better at reaching out and attracting more electrons, right? So this has less space to reach out to try to get a new electron, and so the smaller you are, the more electronegative you are. And again, that has to do with the fact that we saw this pattern during our brainstorm today, that as you go to the right, you have more protons, even though you have the exact same shell. So more protons with the exact same shell means you're going to pull in that shell better, means you're going to get tinier, cuter, and more electronegative. Go ahead one more time, give me green checks, orange X's if that's beginning to make more and more sense. Again, we know the patterns, but we also need to be able to explain how those patterns are related to each other. As we go to the right, we get smaller. As we go to the right, we also get more electronegative, and that is because small atoms can attract more electrons. All right, looking good, everyone. This is going to be the answer to number 8. Again, as we go to the right, we get more protons to pull in the same shell, and so we get smaller and more electronegative. So smaller is the answer for number 8. 20 seconds to fill that in. Capitalization does not matter, but spelling does. Raise your hands when you're good on number 8.
We also learned how that deals with atomic size and how if you're smaller, you're more cuter, and thus you attract more electrons. So go ahead, if you haven't already. Actually, first, if you would like to, just go and tell us how you felt about this lesson. Go ahead and submit your quiz. Tell us how you did. Awesome, Julia. And if after you've done that, be sure to log out if you have no further questions. And we will see you on Friday.